In this video, we're going to discuss the solutions for the final exam in algebra from the fall semester 2018. The exam contains 3 parts, and we're going to go through all of these 3 parts one by one. The first part contains 5 questions on the technical operations over the vectors and the matrices. So in the first question, we're given the 2 vectors and we need to do the following operation. First of all, we need to create these 2 vectors, u plus v into u minus v. So the u plus v vector is going to be the sum of their corresponding entries. It's going to be 1, 1, 0, and 2. To u minus v, it's going to be, so we just need to multiply the first vector to the 2. It's going to be 0, 2 minus 2, and 4. Minus v, it's going to be 1, 0, 1, 0. If we subtract, we're going to get minus 1, 2, minus 3, and 4. So at the end, we just need to multiply them as a scalar multiplication, where we can write this as the 1, 1, 0, 2 vector, because this is going to be the transpose of the u plus v vector multiplied to this, minus 1, 2, minus 3, 4. It's going to be minus 1 plus 2 plus 0 plus 8, which is going to be equal to the 9. In the second question, we need to find the determinant of this matrix, where the determinant of the first matrix P is given, Q is given, and note that P and Q are the 2 5 by 5 matrices. So we are going to use the following rule, that the determinant of the A multiplied to the B is equal to the determinant of the A multiplied to the determinant of the B. So that is why we can split the determinant of the T, P transpose, and Q inverse, and to the multiplication of these 3 different determinants. It is going to be the determinant of the Ti multiplied to the determinant of the P transpose multiplied to the determinant of the Q inverse. So the determinant of the Ti is equal to the 32, since Ti means T multiplied to the identity matrix. It means that it is going to have 5 T's on its diagonal, and obviously its determinant is going to be the multiplication of those entries, which is 2 in the power of 5. So the answer here is going to be 2 in the power of 5. So from the properties of the determinant, it is clear that the determinant of the inverse, the transpose of the matrix, is the same as the determinant of the matrix, which is given, and the determinant of the inverse is the reciprocal of the determinant, which is going to be 32 over 4, which is 8. 8 multiplied to the 5, which is 40. So in a number 3 problem, we need to find the values for the lambda and mu, so that these 2 vectors are becoming parallel. Parallel means we can multiply one of the vectors to some constant and get exactly the same vector as the second one. So here I see that this entry is 2, this entry is 1. In order to make the corresponding, these 2 vectors parallel, I need to choose the lambda to be equal to 2. And I see that here I've got 0. It means that the mu should be also 0. So we've got omega, which is going to be 0, 1 over 2, 1 and 1. If we multiply this to the 2, it is going to be 0, 1, 2, and 2, which is going to be exactly as v vector. So it means lambda is equal to the 2, mu is equal to the 0. Question number 5 is we're given 4 by 4 matrix, and we need to find the multiplication of its eigenvalues. So instead of finding the eigenvalues of the matrix, we're instead find a determinant of this matrix A, which is going to be the multiplication of its 4 eigenvalues. So let's find the determinant. So in order to do this, we're going to go through the second column. So it means we're going to find the determinant of this matrix using the cofactors method. So it is going to be 2 multiplied to its cofactor. So since 2 is in the position of first row and second column, it's going to be cofactor 1, 2. Plus minus 2 multiplied to its cofactor. Minus 2 is in the position 2 and 2. It means that we're going to multiply this to the cofactor C2, 2. So cofactor 1, 2 is obtained by multiplying minus 1 in the power of 1 plus 2 to the determinant of the matrix, which is obtained by eliminating the first row and second column. It is going to be 1, minus 1, 0, minus 4, 2, 6, 9, 0, 2, 3. So we are going to evaluate the determinant of this matrix, again using the cofactor method. Now we're going to go through the third row, for example. So it means that, say minus 1 in a pair of 3 is going to be minus 1, right? So minus 1 multiplied to the 2 multiplied to its cofactor. So the 2 is in the position of third row in second column. It means that we have to multiply this additionally to the minus 1. Multiply to the determinant, which is obtained by eliminating this row and column where it is located. That is going to be minus 1, minus 4, 2, and 9. Minus 1 multiplied to the 3 multiplied to the position of the 3 is 3 and 3. It means that we just need to multiply this to the determinant of the matrix, which is obtained by eliminating the row in the column where the 3 is located. So basically we eliminate this column, and what we obtain is minus 1, 0, 2, 6. So let's evaluate everything. It's going to be minus 1 multiplied to the minus 1 is simply 2. So this is going to be minus 9 plus 8, minus 1 multiplied to the 3, multiplied 2, minus 6. It is going to be minus 2, minus 18, or plus 18, sorry. It's going to be plus 16. So now we need to find the cofactor Ctt. So the cofactor Ctt is obtained by eliminating the row and the column where this minus t is located. So this is going to be Ctt is minus 1 in a pair of 2 plus t multiplied to the determinant of the matrix, which is obtained by eliminating the second row and the second column. That is going to be 1, 3, 4, 2, 6, 9, 0, 2, 3. We can evaluate this cofactor again by going through the third row. That is going to be minus 2 multiplied to the determinant of the matrix, which is 1, 4, 2, 9. So if here we've got the minus because the position of this t is 2 and 3, and the sum is going to be the odd number. Plus 3 multiplied to the determinant of the matrix, which is obtained by eliminating the third row and the third column. It's going to be 1, 3, 2, 6. So the determinant of the first matrix is going to be 9 minus 8, which is simply 1. Multiplied to the minus 2, it's giving you minus 2. And the determinant of the second matrix is simply 0, because 1 multiplied to the 6 is exactly the same as 3 multiplied to the 2. So now we are going to put everything to here. It's going to be 2 multiplied to the cofactor of the C12. It's going to be 16. Minus 2 multiplied to the minus 2, which is going to be 32 plus 4, or simply 36. Let's go through the problems from the second part. The second part contains 5 questions which we need to determine whether the statements are true or false. So please note that when we are going to show that the statement is true, we have to prove this for all possible cases. And if we would like to show that this statement is false, it is just enough to give one counterexample. So the first statement is the lambda is equal to the 0 is the eigenvalue of the matrix. It means that the matrix is not invertible. So which is true. So from the previous problems, we've seen that the multiplication of the eigenvalues is equal to the determinant of the matrix. So if one of the eigenvalues is equal to the 0, it means that the determinant is equal to the 0. It means A is not invertible. So the second question, the eigenvalues of the matrix are always on its main diagonal, which is, of course, false in general. So in general, it is possible to find a matrix whose eigenvalues are not on the main diagonal. For example, 1, 1, 1, 1 matrix. The sum of the eigenvalues of this matrix is equal to the trace, which is equal to the 2. The multiplication of its eigenvalues is equal to the determinant, which is equal to the 0. Which means the first eigenvalue is equal to the 2, the second eigenvalue is equal to the 0. They are not on the main diagonal of this matrix, it means that this is false. So you see, so in order to show that the statement is false, it is just enough to give one counterexample. So the Q is orthogonal. It means that the inverse of the Q is simply transpose, which is true. We can show this, for example, for the 2 by 2 matrix. Q is orthogonal for the 2 by 2 case means that the Q1 and Q2 are going to be orthonormal. Basically, if you multiply the Q1 to itself, it is going to be 1. If you multiply the Q1 to the Q2, it is going to be 0. So let's multiply the Q transpose to the Q. Transpose of this matrix is obtained by writing down the columns of this matrix as the rows. So it's going to be Q1 transposed, which is going to be the first row, Q2 transposed, which is going to be the second row of the Q transposed. We multiply this to the Q, which has 2 columns, and we're going to multiply this matrix row by column. It's going to be Q1 transposed Q1, Q1 transposed Q2, Q2 transposed Q1, Q2 transposed Q2. So when we multiply orthonormal vectors as a scalar multiplication, so this is going to give you 1, this is 0, this is 0, this is 1. It means this is identity matrix, and the multiplication of the 2 matrices is equal to identity if they are inverses. So it shows that the Q transpose is the inverse of the Q. So if R is the reduced row echelon form of the A, then pivot columns of the R form the basis for the column space of the A. So this statement is false in general. And we can show the counterexample for this. So let's take a matrix which is going to be 1, 1, 1, 1. So the column space of this matrix is all possible linear combination of the columns of this matrix, which is simply going to be all possible vectors along this vector 1 and 1. So basically we can draw the line. So the vector 1 and 1 is going to be the basis of the column space. So this line is going to be the column space of the A. So any vector from this line can be obtained as a combination of the 1 and 1 vector. So if we bring this matrix to the row echelon form by multiplying the first row to the -1 and add this to the second, it is going to be 1, 1, 0, 0. This is already the row echelon form of this matrix A. So let us denote this as the R. The pivot column of this matrix is the first column, which is going to be 1 and 0. And this vector is going to be here, 1 and 0. And all the vectors along this vector is going to form this line, which is obviously different from the column space of the A. So the column space of the A is in general different from the column space of the row echelon form of the matrix. So the problem number 5 is to show that this statement is true if the matrix A is orthogonal. So the statement is true, and we can prove this. So the AV and its norm in the square is going to be AV transpose multiplied to the AV. So if you multiply the vector to itself as a scalar multiplication, it is going to give us the length of the vector in the square. So we are going to open up the brackets here by applying the transposition. It is going to be V transpose multiplied to the A transposed multiplied to the AV. Now we can open up the both of the brackets. It's going to be V transposed, A transposed, AV. So since the A is orthogonal, so we know from the previous questions that this multiplication is going to give us the simply identity. It means that this is going to be V transpose to the V. When we multiply the vector, f vector, to itself as a scalar multiplication, it is going to give us the length of the vector v in the square. So we've got this statement to be true. So basically from this equation, we obtain that the AV, its norm, is going to be v norm. So let's go to the problem of the third part. The first question is to find the SVD decomposition of this matrix. So we just need to go through all the steps. So we need to multiply the A to the A transpose. First of all, the A transpose is going to be 1, 0 square root of t, 1, 0 minus square root of t. When we multiply the first row to the first column, we obtain 1 plus 2, which is 3. the first row to the second column is going to be 1 minus 2, which is minus 1. So 1 minus 2 minus 1, 1 plus 2 is going to be 3. So we need to find its eigenvalues. The sum of the eigenvalues is equal to 6. The multiplication of its eigenvalues is equal to the determinant, which is going to be 9 minus 1, which is equal to 8. So it's clear from here that the first eigenvalue is equal to the 4, the second eigenvalue is equal to the 2, since the sum is equal to the 6, and the multiplication is equal to the 8. So the first singular value is going to be the square root of the first number, which is 2. The second singular value is going to be square root of 2. So now we need to find the eigenvectors of this matrix A transpose. So in order to do this, we need to subtract the eigenvalues of this matrix from itself. So the matrix A transpose is equal to the 3 minus 1, and 3. We need to subtract the eigenvalues. Please note that we need to subtract the eigenvalues, not the singular values. The first eigenvalue is 4. We need to subtract the 4 from its diagonal entries. It's going to be minus 1, minus 1, minus 1, minus 1. We are looking for a vector which makes this multiplication to be equal to 0. It is clear from here that if we multiply the first column of this matrix to the minus 1, the second column of this matrix to the 1, it is going to give us the 0 vector. So basically we multiply the first to the 1, first to the minus 1, second to the 1, and we obtain 0, 0. So the first eigenvector is minus 1 and 1. If we normalize this, if we make this as a unit vector, it's going to be minus 1 over square root of 2 and 1 over square root of 2. So we obtain the square root of 2 as the norm of this vector x1, which is going to be minus 1 in the square plus 1 in the square from the square root, which is going to be square root of 2. And we have to divide the square root of 2 we have to divide every component of this vector to its length. So we are going to find the second eigenvector in the same way. It's going to be 3 minus 1, and 3. The second eigenvalue is equal to the 2. Please note that this is 2, not the square root of 2, because square root of 2 is a singular value. If you subtract this, it is going to be 1, minus 1, and 1. And the vector which makes the multiplication this matrix to this vector is equal to the 0 and 0, which is 1 and 1. Simply, if you add these two columns, it is going to give us the 0 column. So the second eigenvector is 1 and 1. If we normalize this, it's going to be 1 over square root of 2, 1 over square root of 2. So the next step is we need to find the v vectors. In order to do this, we need to multiply the A matrix, which was 1, 0, square root of 2, 1, 0, minus square root of 2 to the u1 and u2. So it is okay if we multiply this to the simply u1 or x1. x1 was minus 1 and 1, since we are going to normalize the v1 anyway. So it means that we multiply the first column to the minus 1, second column to the 1, it is going to be 0, 0, minus 2, square root of 2. So if you normalize this, if you make this unit vector, it's going to be 0, 0, 1, right? Since the length of this vector is equal to the 2 square root of 2 multiplied to the square root of 2. Sorry, it should be minus 1 here. So we are going to multiply the A transposed to the x2 or u2. It is 1 and 1. It means we need to add these two columns. It's going to be 2, 0, and 0. If we make this unit vector, it's going to be 1, 0, and 0. On the third step, we need to find the vector v3, the third vector, which is going to be orthogonal to the v1 and v2. And at the same time, it should be orthonormal. It should be a unit vector. So in order to do this, we set v3 to be equal to the a, b, c, where a, b, c are unknowns. We know that v1 transposes a v3 is equal to the 0. v2 transposes a v3 is also equal to the 0. v1 is 0, 0, minus 1 multiplied to the a, b, c is equal to the 0. v2 transpose is 1, 0, 0 multiplied to the a, b, c, which is also equal to the 0. So what we've got is here the equation like minus c is equal to the 0 from the second equation, a is equal to the 0. So we need to set the free variable b to be equal to the 1. So basically, we can write down this equation in a matrix form. It is going to be 0, 0, minus 1, 1, 0, 0, 0, 0, 0. And the first row, the first and the last columns have the pivots, and the second column is going to be the free column. So that is why we are going to set the second variable to be equal to the 1. So the V3 is going to be equal to 0, 1, and 0. So now we're going to put everything together. It's going to be 3 minus 1 minus 1. 3 sigma matrix is going to be 2, 0, 0 square root of 2. V transpose is going to be, we need to write down V1, V2, V3 as the rows of this matrix. It is going to be 0, 0, minus 1, 1, 0, 0, 0, 1, 0. So now we need to find the pseudo inverse of this matrix by writing down the following components. It's going to be, we just transpose the V, it's going to be 0, 0, minus 1, 1, 0, 0, 0, 1, 0. We multiply this to the pseudo inverse of the sigma, which is going to be just the reciprocal of its diagonal entries. It's going to be 1 over 2, 0, 0, 1 over square root of 2. And the U transpose, it is going to be the same as the U, which is 3 minus 1 minus 1 and 3. So let's multiply all of the three matrices. Let's multiply the first two. If we multiply the first matrix, so it has 3 columns. We can do this as the 3 rows, sorry. We can do this as a combination of the rows. So 0, 1, 0, it means multiply the first row to the 0, second row to the 1, third row to the 0, which is going to be simply 0, 1 over square root of 2. So this means we multiply the first row to the 0, second row to the 0, third row to the 1. It means that this is going to be simply 0, 0. This means we multiply the first row of the second matrix as a minus 1, second row to the 0, third row to the 0. It's going to be minus 1 over 2 and 0. We multiply this to the 3 minus 1. Oh, sorry, it should be U transposed. So the U transposed is minus 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, 1 over square root of 2. So we basically can take out 1 over square root of 2 to here. It is going to be minus 1, 1, 1, and 1. It's going to be 1 over square root of 2. So minus 1 and 1, it means multiply the first column to the minus 1, second column to the 1, and add them. It's going to be 1 over square root of 2, 0, and 1 over 2. 1 and 1, it means we just need to add these 2 columns. It's going to be 1 over square root of 2, 0, minus 1 over 2. So if we multiply 1 over square root of 2 to all the entries of this matrix, it's going to be 1 over 2, 1 over 2, 0, 0, 1 over 2 square root of 2, minus 1 over 2 square root of 2. It's going to be the pseudo inverse of the A. We denote this as a A plus. And the last problem of this part is about the matrix operations. So let V is any unit vector from the n-dimensional space. Then we're going to construct the A in this way. And we need to show all of these properties for this matrix A. Please note that the V matrix is the unit. It means that the length of this matrix, of this vector, is equal to the 1, which can be written as the V multiplied to itself. So we need to show directly that A squared is equal to the identity. So the A squared, it means we need to multiply the A to itself, which is going to be identity minus V transpose multiplied to the transpose, multiplied to the I minus V transpose. So we need to open up the brackets. It's going to be identity multiplied to the identity. It's identity multiplied to this one. It's going to be simply TV V transpose. TV V transpose is identity. It's going to be again minus TV V transpose. Minus 2 VV transpose to say minus 2 VV transpose is going to be plus 4 VV transpose multiplied as a VV transpose. So please note that V transpose as a V is equal to the length of this vector V in the square, which is equal to 1. It means that we've got identity minus, so if we add these two terms, it's going to be 4 V transpose plus 4 V transpose, since this two terms in the middle is equal to 1. So which is simply is equal to the identity. So in the B part, we need to show that A transpose is equal to the A. So in order to do this, we're going to get the definition of the A matrix, which is identity minus VV transpose, and simply transpose this. So the sum of the, or subtraction of the two matrices and its transpose, it is going to be subtraction of their transposes. It is going to be a transposition of the A, which is simply I, minus the transpose of the VV transposed. So which is going to be identity minus 2. The transpose of this matrix is going to be transpose of the second one, which is V, multiplied to the transpose of the first one, which is V transpose, which is the same as the A. So if the matrix A, so from the first equation, we see that A multiplied to the A is equal to the identity. It means that the inverse of the A is equal to the A itself. At the same time, we can substitute one of these A's to the A transpose. It means that the inverse of the A is the A transpose. It means that the A is orthogonal matrix. So when the A is orthogonal, the transpose of this matrix is equal to its inverse. So in the part D, so it is stated that the V vector, this vector, which is here in the definition of the A matrix, is one of its eigenvalues. We need to find its corresponding V is one of these eigenvectors. We need to find its corresponding eigenvalue. So the eigenvalue problem can be written as a V multiplied to the lambda V, right? So if V is the eigenvector of the A, we need to show its value of the lambda. So let's simply multiply the A to the V. A by the definition is the identity minus 2V V transpose multiplied to the V. It's going to be V minus 2V V transpose to the V. So we know that the V transpose to the V is going to be the norm of the V in the square, which is equal to the 1, which is going to be V minus 2V, which is equal to the minus V. We're going to substitute this to here, and we obtain minus V is equal to the lambda V. It means that the lambda is equal to the minus 1. In the last part, E part, it is given that some vector omega is any perpendicular vector to the V. We need to show that this omega is eigenvector of this matrix A, and we need to find its corresponding eigenvalue. So let's say omega is perpendicular to the V vector. It means omega transpose to the V is the same as the V transpose to omega is equal to the 0. We need to show that A multiplied to the omega is equal to the lambda multiplied to the omega. So let's multiply the A to the omega. That is going to be A multiplied to the omega is equal to identity minus 2 V transpose multiplied to the omega. If we multiply the omega to all the terms, it's going to be omega minus 2 V transpose omega. So since V and omega are perpendicular, this multiplication is simply equal to the 0, and we obtain is simply omega. So we're going to substitute this to here, and we obtain omega is equal to the lambda omega. Indeed, they are parallel, and they are parallel when the lambda is equal to the 1.